So first, acknowledge my collaborators, Wendy Cho and Yan Liu, both from UIUC and also NCSA. First, quick question: what is GIS? Anybody knows about what GIS is? Raise your hands. Wonderful. So I would argue you are using GIS every day. In fact, as shown on the right slide here, navigation is a basic service based on geospatial analytics and driven very much by geospatial data. That particular pictures from Google-sponsored report published 2013 showing the economic impact of what they call geoservices. Surprising to me when it initially released, this is the economic impact compared to video game industry. It's much bigger. I thought a video game is a much bigger thing. But anyhow, as GIS originally stands for Geographic Information Systems, now S stands for a number of other things. But the main point here is that geo and spatial are special as we're dealing with geospatial computing and the problem solving. CyberGIS, very simple definition here, is GIS based on advanced cyber infrastructure through multiple years of community engagement and also some associated publications just shared with audience potentially be interested in how this definition has evolved. But using some buzz terms to define what CyberGIS is literally tackle big data problems through big computer approach, facilitate big collaboration and solving big problems. In a nutshell, as we've been hearing, the convergence of big data and big compute analytics, CyberGIS in fact is just representing a good example of this convergence. Not only big data to knowledge transformation, but also exploitation of high performance computing. And as you might be able to understand very easily, visualization is a big piece of CyberGIS, as well as teamwork, group-based workflows. And internally, this integration, right, across all these dimensions represents a lot of opportunities for innovation, new problem-solving approaches compared to conventional GIS approaches, and also this user-centric and application-driven considerations. Just to give you a concrete example, because the scientific case taking advantage of Blue Waters is largely contextualized in this spatial optimization class of problems. And this is a study done working with a group of agricultural scientists looking at the trade-off between food security and bioenergy production. The story here is you look at, for instance, Illinois as a production site for crops, food and energy, and the consumers, for instance, might be coming from California or Oregon. And how would you place facilities for refinery, storage, and also evaluate the transportation cost? And conducting a large-scale study like this, you need to run spatial optimization models to figure out the optimal transportation routes and also optimal locations of the involved facilities. This is a very complex problem, requires domain experts, not only GIS people, but also agriculture people, plant biologists, and so forth. But the goal of this study is, in fact, to provide decision-making tools. And under the hood, there's computing-intensive models. In fact, in this case, is running on Exceed resources. But the front end, we assume the users have no necessary knowledge required for working with this environment. It's just a web-based environment. You get into this, you specify your scenarios, you imagine there's unlimited computational power, the data integration from the crops data and the weather data, other dimensions of geospatial data. You don't need to specific knowledge of understanding how the data integration might work. You just work on your scenarios and pose your questions. And once you're done, you're largely interacting with the results in a visual form. And because traditionally GIS users are all expecting their workflows to interact with maps, so interactivity is a big deal in GIS communities. So in our case, although the analysis run in the background are done on supercomputers, we still provide prompt user responses, such as in this case, analysis in the queue or analysis is done. Because this is a collaborative exercise across scientific domains, this wiki system allows different domain scientists to annotate the workflows and the results based on their domain knowledge and evolve that set of domain knowledge. So this is a production service, as you will, for the scientific communities and for the scientific team members involved. You could go onto that URL and get yourself registered. You could actually play with this application. So what's under the hood is this digital environment. I mentioned the Blue Waters, but also XC is what that Bioscope decision-making tool was using. I want to tell you a little bit about this software stack, including 3 major components. As you saw, the Bioscope application was using the web browser-based sort of cloud modality, allows a large number of users accessing that application simultaneously. But also, I'll mention the middleware and the toolkit part just in a moment. The software effort so far is getting supported by this NSF grant, which is a community-wide engagement grant, and includes a number of institutions, but also industrial partner, including Esri. If you're familiar with GIS, Esri is one of the largest players in industry, arguably the largest software GIS company in the world, also contributing their resources and their interest to the project. USGS Geological Surveys agency also matching with their support to participate in this community effort. Gateway, as I mentioned, this is, you could think of as a CyberGIS in the cloud. Behind this user interface is a number of cyber resources, including Exceed resources, as well as Open Science Grid resources, and a few private clouds. This is the user distribution. As you see, it's really representing global community, getting access to a number of scientific problem-solving workflows online. And the GISoft middleware essentially is to manage the complexity of accessing the cyber resources, but also taking into account spatial characteristics to optimize the computation data management. This is essentially for CyberGIS application developers. We hope to have CyberGIS application developers to get exposed to the CyberGIS services at least as easy as they would be exposed to regular GIS services for their application development. So this is an example integrating with mainstream technology from Esri, their ArcGIS Online, shown here through APIs. And the toolkit part, in fact, is most related to our Blue Waters investigation, because this is a community effort, includes a set of loosely coupled open source scalable parallel codes, which I'll delve into further in the rest of my talk. And very interestingly, with regard to this data-driven analytics marriage to high-performance computing, NSF funded last fall this MRI grant, very specifically looking to how to optimize the management of geospatial data and the computing, taking advantage of the CyberGIS tools and capabilities for a number of science drivers. So this is based on roughly 6 petabytes storage, and it's a solid-state drive using that for high-performance data manipulation, but including OpenStack as a cloud component and Hadoop Spark as a big data component, combined with the traditional high-performance computing component, and all of this configured to try to optimize the data manipulation and associated computing. So now getting to the science case, this is, as I mentioned, a spatial optimization case. Spatial optimization has a number of different types of problems. In this case, what we call it's a spatial partitioning problem, right? A particular unit you want to associate to different political districts. In this case, it's a classic case, gerrymandering in North Carolina. As you knew, this is hotly debated over the years in the redistricting process. And associated analytics, if we could abstract all of this into a mathematical form, as I mentioned, it's a spatial partitioning problem. The bad news is as the problem size is getting larger, it's become intractable computationally. Even if you abstract in a perfect way, representing all of this in a computational sensible fashion. And there are also some conditions, as we all know, may not be well captured if you just do the computational part. So heuristics, of course, you run into this challenge, both exact or heuristics. What we chose is a genetic algorithm, which is a heuristics. Not going to delve into details, but the specific contribution here is we believe we have innovation for genetic algorithm to have this spatial GA operators that handles migration that is different from the conventional genetic algorithm. So the idea is not just to parallelize genetic algorithm, but rather think of a new novel genetic algorithm that is very different from the conventional genetic algorithm in a sense that considers migration. So you think of the populations that are evolving. Used to be you would evaluate their fitness in a synchronized fashion, comparing their fitness values, but in our parallel implementation, we consider these populations evolve rather independently. They're exchanging their genetic makeups asynchronously. As we know, the challenges for parallelizing just GA has to deal with this global synchronization. So what we did is to replace that global synchronization with asynchronous communications managed through this buffer strategy at the application level. We hope this kind of strategy might be down level integrated into structure like MPI buffer management, but so far we have to implement at the application level. Getting to feasible solution generation, this is really the idea. You grow spatial seeds and you manipulate the association of different spatial units. As you can imagine, this is astronomical number, different options you have to go through working with different geometries. Scaling is pretty good because we basically eliminated the global synchronization. This is perfectly asynchronous, and it's almost, you could imagine, in the next blue waters, we could have taken advantage of the scalability without any expected trouble. But the better news is because we argue this is a fundamentally new genetic algorithm, you are getting to new solutions. And also solution quality tends to be improving as well as you increase the number of cores. So the algorithmic behavior is now different from the sequential genetic algorithm because of this asynchronous evolution of massive populations. So back to the North Carolina example, as we all know, this is a well-studied state in political redistricting. And the ideal situation, you want to go to as fine as possible to your spatial granularity. Right now, we're still working on the voting districts, but possible scenarios, you could go to census tracts and blocks, even finer granularity. That even poses greater computational challenges. So this might look unfamiliar to you, right? This is not a classic result when you do redistricting, but this is a feasible solution. But there are that many feasible solutions. So this is a big data analytics problem. When you have that many feasible solutions, how would you evaluate, right? What is the best results or best configurations to different constituencies? And how public or politicians, they need to know there are such feasible solutions and possible scenarios. Right now, as you might imagine, all this knowledge is perhaps not well discovered. And we argue this is limiting the democracy in a number of ways. So back to the story of CyberGIS, as you might be able to tell, CyberGIS communities are rather diverse. The social science example I presented is just one example, and it's getting enormously benefited from the access to Blue Waters, but there are other communities. Both the communities are advancing CyberGIS itself, but also user communities as well. And we started this CyberGIS Fellows program, which is different from the Blue Waters Fellows idea to some degree. And this is a number of junior faculty that are developing learning materials across campuses mapped there. The idea is as the CyberGIS community getting the next generation exposed to big data and big compute approaches, we need a whole new generation of learning materials produced. And this is the first attempt to produce that set of materials so that that could be quickly through these junior scholars getting into the hands of the students so that they become equipped to also deal with the kind of interesting problems I was talking about, such as the redistricting example. So with that, I want to acknowledge NSF, the grants supporting our work, and be happy to take any questions if I have time. Thank you.
Take questions while we're getting set up for the next speaker.
Yes.
So you have a lot of feasible ways to do the districting, and I was just curious how you compare which ones are better than others.
Yeah, so there's one slide I did not delve into details. There are maybe 4 to 8 key criteria. Population is a major one. Each district has roughly same amount of population. But there's also compactness, meaning, for instance, the general mandarin cases, you have literally your district is going across a highway, right? That is based on spatial measurement, not very compact. That somehow is also included into consideration of the legal processes, determining whether this is reasonable or not. But there's a racial composition. So there are a number of such criteria getting considered in the redistricting process. Therefore, as I mentioned, although we might be able to formulate this computationally and computing them in an attractable fashion, but when it's combined to practice, there are still some ill-structured aspects we have to be. Bob.
Being from North Carolina, Washington,
Okay,
completely throw out all of your reasonableness.
Yeah.
That's not how it works. And no, the thing is, there's a Supreme Court decision that said that it was so unreasonable that they had to go back and redo it. So, but this idea of being able to put reasonableness into other social systems, at least you can argue that they don't have the excuse that there isn't a reasonable solution.
Yeah.
That the only way to do it is to do it by hand and gerrymander the districts. So.
Well, there are currently GIS helping politicians and stakeholders to do this. But our argument is that there are much, much bigger, massive solution space, from scientific point of view, that would benefit not only those people, but also general public. We think that is valuable to democracy. Scientifically, we don't argue this would be directly practical to the political process itself. And as you said, right now it's very much closed door kind of process.